So we're going to look at the relationship between continuity and differentiability. What we want to be able to do is to say that there's a relationship between the continuity and being differentiable. So we're asking, if the function's continuous, do we know that it's differentiable? Or if it's differentiable, do we know that it's continuous? This differentiable is just asking is, can we find a derivative at that point? So let's take a look at these three functions to see. Um, we're going to begin by graphing them, and I've got my graphing calculator to be able to do that. So let's put this in the graphing calculator to be able to see what exactly the graph looks like. So get the square root of x squared minus 4, and we can graph that. And I'm going to come over here to the side, and I'm just going to draw a sketch of this graph. Something like that. Now just know that this is a portion of the graph from a hyperbola. You may remember that from your Algebra 2 days. So based on this graph, is f continuous at 2? Well, we see that f of 2 exists. It has a value of 0. But you have to remember back to the formal definition of continuous. Continuous said that the limit had to exist. Well, in order for the limit to exist, the limit from the left and the right had to exist. So if we're coming into 2 from the right, no problem. That's going to exist. Coming in from the left at 2, it's not going to exist. So this is not continuous. Only at x equals 2, because the limit as x approaches 2 does not exist. Does not exist. Now, let's look at it from the derivative. Okay, I'm going to rewrite it with my fraction exponent. So I can take the derivative. So I'm going to bring that 1/2 power in front. I'm going to decrease the power by 1. And then I'm going to multiply by the derivative of the inside. So the derivative of x squared minus 4 is 2x. Clean it up just a little bit. Notice your 2's cancel. So you have x on top, and you have this square root of x squared minus 4. Now, let's see what happens when we plug in 2. If I put 2 in for x, in the numerator I get 2. In the denominator I get 2 squared minus 4, which is 0. That tells me the derivative at 2 does not exist. Now you may be asking yourself, well, what does that mean? I'm glad you asked. What this means is that if we're not continuous, then the function is not differentiable. If the function is not continuous, then it is not differentiable. All right, so that's one scenario we know. We know a connection now. Let's see if we can discover some others. Let's look at the second function I have here. This time we're considering the function x to the 1/3 plus 2. Let's put that one in and see what we get for a graph. So I've got x to the 1/3 plus 2. And let's take a look at that graph. It's a classic cube root graph, shifted up 2. So ask yourself, is it continuous based on the graph? For this one, I would have to say yes. F of x is continuous at x equals 0 because f of 0 equals the limit as x approaches 0. So remember, your continuity definition says the function must exist, the limit must exist, and the function and the limit must be equal. Now let's find the derivative. So the derivative of x to the 1/3 would be 1/3 x to the negative 2/3, which we could make that a positive exponent by bringing it to the denominator. But watch what happens when we put in 0. We get 1/3 times 0 to the 2/3, which is 0, which tells us that the derivative at 0 does not exist. Now, wait a minute. This one ended up being continuous, and yet the derivative did not exist. So when does that happen? So functions with vertical tangents, which is what we have here, we have a vertical tangent at x equals 0 and sharp turns are continuous but not differentiable. So we have to watch for those because they're tricky. They're continuous, but they're not differentiable. Okay, let's look at one more scenario. This time we're going to put in x to the 2/3 plus 2 and take a look at that graph. Looks very, very similar, right? Mine's sketch is not perfect, but that's okay. So let's answer the question. Is it continuous? The answer is yes. F of x is continuous at x equals 0 because same reason, right? The function at 0 equals the limit as x approaches 0. All right, let's see if it's differentiable. We'll take the derivative of x to the 2/3. That's 2/3 x to the negative 1/3. Move it to the bottom, clean it up just a little bit, but watch what happens when we put in 0 again. We still get that does not exist, right? So look at your graph. Why did it not exist? Didn't exist because there was a sharp turn there. We had a sharp turn. And when should we know vertical tangents and sharp turns, they're continuous, but they are not differentiable. So let's summarize. So based on what we've seen, does continuity imply differentiability, or does differentiability imply continuity? Well, we've already shown that you can be continuous but not differentiable. So it has to go the other way. Differentiability must implies continuity. Meaning, if you are differentiable, then you are continuous. So in order for a function to be differentiable, the function must be continuous. And the function must have no sharp turns or vertical tangents. So we've got to look for these things. We've got to check, is it continuous? Is there a sharp turn or a vertical tangent? So look at the piecewise function I have here. Is it continuous? We got to go back to our continuity rules, which told us that in order to be continuous, the limit has to exist and the function has to equal the limit. So let's find out if the function exists at 3. So find f of 3. G of 3. So G of 3, we would plug into this first piece because I see the equal sign there. So that would be square root of 3 plus 1, which would be 2. G of 3 exists. Does the limit exist? Well, when you're dealing with the piecewise function, you've got to check the right and left-hand limits. So the limit as x approaches 3 from the right would be the first piece in your piecewise function. And the limit as x approaches 3 from the, and I said that backwards. The limit as x approaches 3 from the left would be your first piece. And the limit as x approaches 3 from the right would be your second piece. Let's see if these are equal to each other when we substitute in 3. And they are. When that happens, the limit equals the functional value, then we say yes, g of x is continuous at x equals 3. And we showed our analysis here. Now, to determine if it's differentiable, when you have a piecewise function, you obviously have to take the derivative of the pieces. So the derivative of square root of x plus 1, we probably want to think of that as x plus 1 to the 1/2. That would be 1/2 x plus 1 to the negative 1/2 between 0 and 3. I'm intentionally leaving off the equal because I'm not sure if it's equal there. Then the derivative of the second piece, the derivative of 5 minus x would be negative 1. Now we need to check these pieces to see if I get the same value when I do the left and the right. So I'm just cleaning it up just a hair. Let's find out what the derivative at 3 from the left would be 1 over 2 times 3 plus 1 to the 1/2. 3 plus 1 is 4. 1/2 power would be 2. So I get 1/4 here. Derivative at 3 from the other side gives me negative 1. So I know that g of x is not differentiable at x equals 3. And I just showed why, because I take the derivative and I get a different derivative from both sides of 3. Okay, these are the more common questions I see on the AP exam. They ask us for a value that would force the function to be continuous and differentiable. Let's deal with the continuous part first. We know that the limit as x approaches 3 from the left would come from the first piece. And that, in order to be continuous, must be equal to the derivative from the right of the second piece. Let's plug those in, 3 for each side, very similar to what we did in the previous problem. And I want you to see that this basically didn't get me anywhere, okay? But it gave me an equation with k and m in it that I can use. Now, let's do the same with the derivative. Remember how we were going to write that in the last piece? So my derivative would be k times 1/2 x plus 1 to the negative 1/2 for the first piece. And then my derivative for the second piece is just going to be m. It's the coefficient of x. So now I know in order for this to be differentiable, this first piece, which I'm going to write as k over 2 times x plus 1 to the 1/2, must be equal to m when x is 3. So let me put the 3 in there. So 3 plus 1 is 4 to the 1/2 power is 2. 2 times 2 is 4. So I've got k over 4 equals m, or k equals 4m. Now, you may be saying, well, that didn't tell me anything. It actually did, because I want you to see you now have two equations with two variables. When you have two equations with two variables, you can use substitution or elimination. I'm going to substitute 4m for k, and I'm going to solve. Because now I have 8m equals 3m plus 2, which is 5m equals 2, and m equals 2/5. That tells me the value for m that I need. And then I can come over here to k, and I can sub in 2/5 for m, and I know that k has to be 8/5. And that's how I see this concept showing up on the AP exam a lot, playing on the continuous and differentiable. Now, if you look at the last question we're going to deal with here, it just asks us for what values of a and b is the function differentiable. They really only ask for one. The reason is because we know differentiability implies continuity. So if we know something's differentiable, we know it has to be continuous. So we go at the same approach. Let's do the limit first for the continuity piece. We know the limit as x approaches 1 from the left. We'll use our first piece in our piecewise function. And that the limit as x approaches 1 from the right, we'll use the second piece. Let's make our substitutions with x being 1. That's going to be giving me 3a plus 2b plus 1 equals a minus 4b minus 3. Now, just to get ready, I like to go ahead and get all of my a's and b's on one side. So we'll subtract the a, and we'll add the 4b, and then I'm going to move the 1 over here. So I've got my equation very much like I did in the previous problem. Now I'm going to go use the derivative piece. So I know that f prime of x would be take the derivative of each piece. The derivative of 3ax squared would give me 6ax plus 2b. That's when x is less than 1. And I know that this piece, the derivative would be 4ax to the third minus 8bx minus 3. And remember, these two pieces have to be equal to each other when x is 1. So when x is 1 on the first piece, I get 6a plus 2b. And when x is 1 in the second piece, I get 4a minus 8b minus 3. Now, just like I did before, I'm going to get all of my a's and b's on one side. So I'm subtracting that 4a. I'm adding that 8b, and it's going to equal negative 3. Now, for this one, because there's coefficients involved, I'm going to use elimination. So I'm going to take 2a plus 6b equals negative 4. And I'm going to take 2a plus 10b equals negative 3. I'm going to distribute a negative to this second equation, which essentially changes all the signs. The reason I do that is because I want to eliminate the a's. You'll notice very easily when I add these two equations together, the a's eliminate. I'm left with negative 4b equals negative 1. So b is 1/4. Now, you've got to go back to substitution. Take either of the equations you have and substitute in 1/4 for b. So I've got 3 halves here. Notice 6/4. Made it a little easier. So I've got 2a equals now negative 4 minus 1.5 is going to give me negative 5.5. That's a negative 11 halves. So a is negative 11/4. So I've got my two values now for a and b. But again, remember, these last two problems, that's how we see it most often on the AP exam. So keep practicing with these. Let me know in the comments if you have any questions or you'd like to see another one like that. I'd be happy to do that. Thanks so much.